Today, we're diving straight into the absolute nervous system of a utility-scale solar plant. We're going to use a blueprint-style breakdown to map out the entire electrical network. We're talking the crucial AC low voltage and medium voltage networks, the immense DC cabling, and the intense testing that makes sure this whole massive facility doesn't just, well, melt into the sand. This is exactly where high-level math meets heavy-duty field engineering. Here is our game plan for today. We'll be sizing the cable network, looking at the trenching and installation rules, connecting up the medium voltage infrastructure, and finally, running through the factory and site testing. All right, Section 1, sizing the cable network, the blueprint math. Okay, so before a single shovel even hits the dirt out on site, we have to mathematically prove our network won't fail. This takes us right to the design lab. The math here is the absolute foundation of the plant's efficiency and safety. You've got these three mandatory checks: current carrying capacity, voltage drop, and short-circuit thermal rating. Every single engineer must rigorously calculate these for every DC, AC low voltage, and AC medium voltage cable. Whether we're talking about a massive medium voltage feeder running to the switchgear or just a smaller low voltage cable coming off an inverter, it has to pass these three gates. Because if a cable fails even one of these, you're risking massive power loss, catastrophic equipment damage, or worse, a massive electrical fire. I actually love this first concept, derating the current carrying capacity, or CCC. You know, out in these blistering hot desert environments where ambient temps can easily hit 40 or 50 degrees Celsius, a cable's raw out-of-the-box capacity drops dramatically. You absolutely cannot rely on standard factory specs out there. You have to mathematically derate it. This means applying very specific reduction factors for things like the ambient temperature, how tightly the cables are grouped together, and the thermal resistivity of the soil itself. It's the only way to ensure your cable survives the harsh reality of the environment while safely handling the maximum string current. Moving to check number 2, the voltage drop, or VD. We hit a seriously strict threshold here, 1.5%. Now, for your low voltage connections, you might occasionally see engineering allowances of up to 3 or 5%, depending on the plant. But for your primary power arteries, your DC string cables, and those massive MV feeders, hitting this 1.5% mark is critical. It literally stops catastrophic power bleeding over long physical distances before the energy can even reach the utility grid. It's a make or break number for the financial viability of the whole gig. And that brings us to the third check: short-circuit thermal survival. Basically, if a massive fault happens, the cable has to survive an intense thermal spike for the fraction of a second it takes the breaker to trip. Check out how the math changes based on your conductor material here. Engineers use a constant, denoted as K, of 143 for copper and a much lower 105 for aluminum to calculate the minimum safe cross-sectional area. It proves that even during a worst-case electrical fault, your cable won't literally vaporize before the safety systems can kick in. Moving right along to Section 2, trenching and installation roles, digging the pathways. So how exactly do we safely separate all these varying voltage levels underground? I mean, burying thousands of meters of cable isn't just about digging a random hole, right? Comparing the installation requirements for multiple types of cables reveals a huge safety principle. Because AC medium voltage cables carry vastly more hazardous energy than standard DC solar cables, they demand much deeper trenches, a full 1.0 meter depth minimum, plus significantly wider bending curves. This prevents insulation stress and physical crushing under the weight of passing maintenance vehicles. Meanwhile, the lower voltage DC cables only require a 0.6 meter depth. Think of an underground trench like a highly engineered sandwich. You definitely don't just toss the cables in the dirt and call it a day. Starting from the bottom up, the cables rest on a precise 10-centimeter bed of pure sand, so they don't scrape against sharp rocks. Then, they're laid completely flat with exact separation gaps, and covered in another 20 to 30 centimeters of sand. Next comes the armor, rows of protection bricks. You're looking at 8 bricks per meter for the critical MV lines and 2 per meter for LV. Top it all off with bright danger tape 30 centimeters above the cable, and finally, compacted topsoil. Every single layer has a vital job. Now pay close attention to this strict 50-centimeter physical separation rule on this site checklist. Space is usually super tight in these trenches, but if you absolutely have to run AC and DC lines near each other, maintaining this half-meter buffer is completely non-negotiable. It physically stops the powerful alternating magnetic fields of the AC circuits from interfering with or inducing harmful currents right into your DC lines. And of course, we literally cannot forget the brains of the operation, the SCADA and communication layout. These incredibly sensitive fiber optic data lines monitor every inverter, transformer, and breaker out there. Because they're so essential, they get their own dedicated routing rules to stay completely interference-free. That means separate, totally weatherproof, clearly labeled conduits, and a solid half-meter burial depth just to protect the delicate glass fibers inside from physical shock. On to Section 3, connecting the MV infrastructure, the true heart of the plant. All right, so our massive cable network is mathematically sized and safely buried in the dirt. Now it's time to connect the heavy machinery that actually steps the power up for the grid. Looking at these specs, our power transformer kiosks take the AC/LV, usually around 0.8 kilovolts, and dramatically step it up to a 33 kilovolt MV output. And right alongside those heavy-duty specs, notice the universal green, red, and flashing amber color codes on the control panels. These mimic circuits give operators an instant, universal signal if a breaker is safely closed, open, or if a critical trip just happened. Right inside these stations is a crucial piece of hardware, the ring main unit, or RMU. Think of the RMU as the ultimate local bodyguard for your transformer. Since it's handling massive MV power, 33,000 volts, it uses a highly pressurized, sealed metal enclosure filled with specialized SF6 gas. This gas is an incredible insulator, letting the unit instantly extinguish dangerous electrical arcs in a fraction of a second, actively preventing catastrophic explosions right out in the field. If we zoom out a bit, look at how we're connecting loops back to the MV switchgear. This loop-fed configuration is just a brilliantly smart, built-in failsafe. By wiring that 33 kilovolt feed through the RMUs in a continuous loop that eventually returns to the main switchgear, you create amazing redundancy. If one specific feeder goes down for maintenance or a fault, the power simply flows backward through the alternate loop. That means you don't have to drop the entire multi-megawatt array completely offline just to service a single transformer. This comparison really highlights how the massive, centralized MV switchgear differs from those localized RMUs scattered around the blocks. The main switchgear is your central hub. It uses heavy-duty vacuum circuit breakers, or VCBs, to manage and protect the massive combined power output before it shoots out to the utility grid. On the flip side, the compact RMUs act as your field guardians, using their sealed SF6 enclosures and load break switches to sectionalize specific, smaller parts of the array. Which brings us to Section 4. Factory and site testing, the final exams. Okay, so you've done the math, you engineered the trenches, and you've wired the heavy gear. But there is no way the utility grid operators are letting you send a single watt of power onto their grid until you pass these tests. Now, there are two wildly distinct phases here. The factory acceptance test, or FAT, happens thousands of miles away at the manufacturer's facility. That catches wiring or workmanship defects before anything is loaded onto a ship. Then the site acceptance test, or SAT, happens right out there in the dirt to prove your construction team actually built and integrated it all flawlessly under real-world conditions. Take a look at this actual FAT checklist for a power transformer. Engineers take this stuff incredibly seriously. During these dielectric tests, they are literally blasting the equipment with 70 kilovolts of alternating current. They do this just to absolutely guarantee that the internal insulation won't suddenly flash over or break down when it faces worst-case electrical stress in the real world. Fast forward to the site, and the SAT follows this completely unforgiving timeline, from rigorously checking the insulation resistance with Megger testing, to simulating relay trips, to finally verifying all those SCADA data links are actually live. This strict sequence forces the team to prove the plant's protection logic works flawlessly, because one single mistake, or one bypass step here, live grid power could literally destroy the entire system the exact second they flip the switch. Notice how the SAT specifically zeroes in on worst-case scenarios. Field engineers use these specialized test kits to artificially inject highly dangerous faults like severe overcurrents or earth faults directly into the system. The whole goal is to make sure those precise protection relays trip the massive circuit breakers exactly when they are supposed to, in milliseconds, sending those vital timestamps back to the control room. It proves the safety loop is completely airtight.